All right, hello friends. We are going to take a look at rational applications of rational functions, I should say. So we'll do two examples here. So first one is about the Game Commission introduces 100 deer into newly acquired state game lands, and the population of that herd is modeled by this rational function. So T is measured in years, and we want to find the population when after 5 years, 10 years, and 25 years. So simply, all you gotta do is plug the numbers in. So for part A, for plugging in 5, I'm just going to plug in 5 everywhere I have the variable t. Be very careful with this. Whenever you have a rational function, you want to make sure that you put parentheses around that numerator and denominator. It's best to kind of play it safe and to just evaluate the numerator, evaluate the denominator, and then just divide it out. So this comes out to be approximately 333 deer after 5 years, and you'll repeat the same thing for the other number of years. So for 10 years, all I'm going to do is plug in 10 everywhere I see a T. What I would encourage you is make sure that you're able to do this on your calculator. Because oftentimes you'll find out that when it comes down to the quiz or the test, if you never practice how to enter this in and make sure that you're getting these values, then it's not going to be good. After 25 years, you have about 800 deer in that population. So the population did grow over time. For part B, it says, I believe, what is the limiting size of the herd? So what that means is what number does the population approach? So at some point, does that population level off? So this is kind of best illustrated when you look at the graph, but if something's approaching a value, it's approaching a horizontal asymptote. So what we want to do is find that horizontal asymptote. So how do you find a horizontal asymptote? Hopefully you know. You compare the degrees of the top and the bottom. So my degree is the same on the top as on the bottom, but be very careful. I want to distribute that 20. So if I distribute the 20, I would really have 100 plus 60t. So my horizontal asymptote is going to be the ratio of those leading coefficients. So I have a 60 in front of my variable on the top, and I have 0.04 in front of that variable on the bottom. So if you divide those out, that limiting size is about 1,500 deer. So I do want to show you the graph. So on your graphing calculator or on Desmos, I'll show you the graphing calculator in class. I don't have the graphing calculator app on my computer. So I already have it pre-plugged in. When you type it into your graphing calculator, you have to put parentheses around your numerator and your denominator. Rational functions always need a hug. The numerator needs a hug. The denominator needs a hug. So for this, when you plug this in, I kind of tweaked my X and my Y axis. All you'd have to do is you click the wrench. And so X is time. So I played around with it at first. I did like looking at what it looked like after 100 years. And then I kept increasing that. So I think I ended up doing like 500 years. And then I could really see really clearly that it was leveling off. And as far as my Y-axis, that's telling me my population. When I looked at the values that I had got for part A, I had like 800 deer. So that kind of gave me a hint on what I should try for playing around with the Y-axis. And the thing about your graphing calculator and Desmos is you can keep changing that window. So on your graphing calc, you'd hit window, and that's how you change what you see on your X and your Y axis? I feel like an influencer. On your window. But for this, you can see that by hand, we found the horizontal asymptote was at y equals 1500. And you can see that the function is approaching it. So what that means in terms of the context of this problem is that population is leveling off at 1500. Arthur, do you have anything to say? No, he came to say hi. He's very friendly today. Stay tuned for the next video.